to. Hello everyone, IKX Talks, the 9th time with this. We are very glad to have all of you here, Connect World and the Universe. Actually, IKX Talks, we became one part of the PKU's Global Open Talks. You know, PKU's Global Open Talks, named as X License, was started this Wednesday. They invited many top scientists and speakers to talk about different topics. So yeah, for this new series, please be sure, to follow PKU's, online talks. And every Wednesday, that's 8 o'clock. So this was a series talks was co-linked with ICANX talks. That will cover much more topics than not just science. So, and we know that this week was special for ICANX talks because this week we have ACS Nano Rising Star in nanoscience and nanotechnology. How this going on? How to get all these ICANX talks? Now we have Professor Paul Weiss, who is chief editor of ACS Nano, and he is also the founder of this journal. He has the stories to tell. Paul. Yeah, the stage is yours, please.
Thank you so much, Alice. I don't know if I'm up there yet. Well, I'll just go ahead and talk. We're delighted to join with you from the start of the ICANX lectures. And one of the things that we normally do in the world is go to conferences, visit universities and research institutes around the world, and we're able to ask our hosts and our friends to help us identify the up-and-coming researchers at those places. In this time when our travel is restricted, we've been looking for another way to find the groups that are the future of nanoscience and nanotechnology. So it's been wonderful to join with you and with our editors to help find the people who can lay out what's to come, to highlight their work and to introduce them to the world in a way that they also are not getting the opportunity to do because travel is so restricted. So this is the first round of Rising Star lectures, and today we'll have Miso Kim from the Korea Research Institute of Structure and Science. We'll have Nanshu Liu from University of Texas at Austin, and Wei Gao from Caltech. In addition to the lectures that they give, we'll ask them to write perspectives on where they see nanoscience and nanotechnology going in their fields, and we'll also ask for their continuing advice in an advisory board of Rising Stars. And so we're really delighted to have them on board at ACS Nano to work together with you. And you see editor Yuri Gagotsi here and our other editors around the world in helping identify these rising stars. And we're really looking forward to these lectures and the enormous global platform that you've been able to put together for us. And so I think what I'll do now is turn it over to Yuri to introduce our first rising star. This is Yuri Gagotsi, a world famous materials scientist, leader, and pioneer at Drexel University in Philadelphia, Pennsylvania, on the East Coast of the United States.
I think I've been muted, sorry. Good morning to everyone in America. Good evening to everyone in Asia, and good day to our European, African, Middle East colleagues. It is my pleasure to introduce the first ACS Nano Rising Star lecturer, Dr. Miso Kim from Korea Research Institute of Standards and Science. You might have listened to talk by Professor Zhonglin Wang about energy harvesting in the very beginning of this lecture series of ICANX talks. And With this presentation from Dr. Miso Kim, we kind of continue in the topic of harvesting energy. And Miso is a senior research scientist at Korea Research Institute of Standard and Science, KRISS. But she received her undergraduate degree in material science and engineering from Seoul National University, a top institution in South Korea. And she continued toward master's and PhD degrees in material science engineering again, studying at the Massachusetts Institute of Technology, famous MIT on the East Coast of the United States. After graduation, she joined KRISS as a senior research scientist in 2012. And she has been pursuing research on analytical modeling, design, experimental characterization of piezoelectric material, smart structures, including metamaterials, for energy harvesting as well as sensing applications. She is a young rising star, but she has already led major research projects in Korea. And with this, I give the word to Dr. Kim, who will tell you about her exciting research. Welcome to the talk.
Thank you so much, Yuri, for introducing me very nicely. I'll share my screen first. Okay, I think I can see myself on top of the podium and with my slides, okay. Okay, I'm going to talk today. I'm Miso Kim, Smile Kim. You can see the Chinese character of my name as well. And I work at KRISS right now. I introduce KRISS a little bit later. So today, as Yuri introduced already, I'm going to talk about the metamaterial-based energy harvesting, energy focusing, energy harvesting. So energy harvesting is the research topic that Professor Zhongmin Wang already addressed very nicely. He's the founder of the nano generator, and he's the big guy in energy harvesting. And about the metamaterials, you've already heard of the optical metamaterials from Professor Nicholas Fang at MIT in this series of talks as well. But at the end of his talk, he talked about the acoustic metamaterials to cancel the noise a little bit for about 10 minutes. So you can go back to their movies again after my talk if you're interested. So I'm going to talk about technology where we can merge these two interesting, two attractive, these two technology, metamaterials and energy harvesting are merged together. And before I go on, I'd like to introduce the National Institute where I work, the Korea Research Institute of Standards and Science. So for those who may not be familiar with here, KRISS, KRISS is the Korean version of National Meteorology Institute. So like NIST in the United States, and I searched it, and I am in China, National Institute of Meteorology. So here, this is the main gate I pass by every day, and we are located in the center of the South Korea. So if you are familiar with Seoul, the capital here, then I'm now here and speaking to you. So I think this is the best way to start with my lecture, with my talk, with this picture, for two reasons. First, this is where I met Alice. That's why I'm so fortunate to be selected as the first speaker of this ACS Nano Rising Star today. And I met her here. And the other reason is that energy harvesting is the very topic, the research topic that connect us at this conference. And here we gave a talk together and got to know each other. So energy harvesting is my beloved research topic, but we start with, we need to, I want to talk about why we need this energy harvesting technology first. So, So as far as I know, a lot of cities launched those very nice programs for smart cities, and everybody's pursuing like smart cities. Everything is connected, smart life, and everything. So the key word here is the getting connected, and then everything is connected. So connectedness. In order to connect everything, what we need is the Internet of Things, so that we can connect everything. The essential part of the Internet of Things are sensors. So we need to detect something from our own body, or from animals, or from our routines, or like industrial sites, or signals from the environment, so that we can connect, we can send some signals and get connected. But the problem is, we use power sources for these IoT sensors with batteries. Batteries are very nice and great, but if you use batteries in certain places inaccessible, we need to replace them with high cost and with high danger too. So if we can you can use some self-powering system like energy harvesting for IoT sensors, then it will solve some problem, and a lot of necessities are out there for energy harvesting for this reason. So energy harvesting is a technology that that can convert ambient energies existing in nature, in our daily life, and in industrial sites, otherwise wasted, into electrical energy. Right now, I'm talking to you and I'm making some sounds, but sound is going away. Of course, I'm conveying some messages, but it's going away. So it's not converted into electrical energy, but if I use them if I use them to convert them into electrical energy, that's an sound energy harvesting technology. So you are looking at the bar here, and then it's representing the potential power levels that each energy harvesting sources, or these different energy harvesting sources, can generate. So I'd like to point out that so there are so many kinds of energy harvesting technology depending on the sources, and then these energy harvesting technologies are not competitive with each other. So instead, depending on the target applications, what we can do is we can choose energy harvesting sources. If you need a megawatt like a power level, then you can choose wind energy harvesting. But here, what I chose is mechanical energy harvesting, because that can generate like very small power ranging from milliwatt to microwatt levels. And that's what we need for powering IoT wireless sensor networks. It's a very attractive technology, the mechanical energy harvesting, and I've worked on it like for, I guess, more than 15 years now, but still we have so many issues. It's a pity, but at the same time, it's a luck for me, because I have a lot of work to do from now on for a while. So the first thing we need to solve is performance. Since although we've experienced a lot of enhancement in power performance from energy harvesting for the past decades, still we need to increase more voltage and more power, and the significant problem lies in the current level. So we need to increase the current levels out of the mechanical energy harvesting. In terms of the mechanical performance, we have to think about the reduction in resonant frequencies. The vibrations, or those mechanical waves, the characteristics are like this. So what we make from vibrations has a very low frequency levels. But the thing is, if you want, and at the same time, we want to use a very small sizes of devices. Intrinsically, small size devices have a very high frequencies, but at resonances, they can generate the maximum power. So if you want to match the resonant frequencies if you want to align the resonant frequencies between the nature and then the natural sound, energy harvesting sources with our devices, we need to find a way to reduce the resonant frequencies, and which I did a little bit with adding the mass. And we want to operate these energy harvesting devices in a wide range of frequencies. But as I said before, at resonances, the power is maximized. And that means at off resonances, we have very reduced power generation. So that's why we need some more broadband, energy harvesting designs for broadband operations. And unlike solar cells or thermoelectric generators, we don't have a standardized that set together all over the world as a figure of merit for vibration energy harvesting or the mechanical energy harvesting yet. So we need to work on the standardization problem as well. So once we achieve a certain level of performance, the next thing we have to think about is reliability. Since we are using the moving structures to generate the energy out of mechanical energy harvesting, the first fatigue can come from structural fatigue. And the other thing is we are using piezoelectric or triboelectric functional materials, so we have to think about the piezoelectric degradation. At the same time, we have to think about using a selection of lead-free materials. The reason is that the most high performance the highest performance piezoelectric materials are based on lead. People have tried to develop the lead-free materials which have equivalent or enhanced properties more than lead-based materials, but it's still challenging. So these are the issues. But today I'm going to focus more mostly the performance of the mechanical energy harvesting. In order to enhance the energy harvesting performance in terms of power, we have to look at the energy flow mechanisms like here. So if there's a vibrations, we want to make the vibrations being absorbed as much as possible into the devices first. That's the first step here. And the first step is it involves the optimizing of device designs like here. So in terms of geometry, you can make a circular one, you can make a triangular one to make the efficient absorption from mechanical to mechanical. Once we have a structure and the device has the mechanical energy inside, then it needs to be converted into electrical energy. So for that, what we need is high efficient materials, piezoelectric materials, or the electrode materials that can support, or structural layers that can support the piezoelectric materials for high efficiency conversion. And once we generate the electrical energy out of the conversion devices, then we lose a lot across the power management circuit. For that, we need a really customized energy harvesting circuit designs like here. And at the end, what we have as a target application like sensors, if we can have a low power electronics, then we can mix at certain point. We have a small power generation and they need only small power, then we can have practical applications like here. So there are three approaches in three categories for energy harvesting power performance enhancement. So in terms of these regards, what I did for the first time as energy harvesting researcher was the development of analytical model that can predict the performance of the energy harvesting performance, voltage and power of the vibration-based piezoelectric energy harvester. So we developed the analytical model very accurately, and what the model can do is that we can predict where the power, is the position the power can be maximized. So power can be maximized at resonances, but the important message here is that it can shift. So when you connect the energy harvesting devices to the electrical circuits or your target applications, there's an electrical impedance connected. Then the electrical impedance influences the position where your resonance occurs, and that means you have to tune your device. You have to design the device again according to the resonance point. So that's what the predictive model can do. So we experimentally verified, and so that we can confirm the predictive capability of these models we developed. So we extended our work to see the output harvesting performance depending on the selection of electrode configuration. For example, even if we use the same piezoelectric material like here, if we use the capacitor type electrode like here, or depending on the selection of electrode configuration like capacitor type or interdigitated type, even with the same piezoelectric layer and same structural layer, it can yield different levels of performances. That's what we've studied. And the other thing we can do is, I've mentioned a little bit already, we put masses at the end of the vibrating cantilevers or other structures to reduce down the intrinsic resonance frequency of the energy harvesting devices. But depending on the size of the proof message, the analytical model we have to use to predict the performance of energy harvesting system is different. That's what we showed analytically and experimentally as well here. So we looked at the environmental condition as well. So the nature has a very random vibration characteristics. Even in the random vibration signals, we can categorize into three kinds like here. So the first thing is the only amplitude changes with time. The next thing is frequency changes with time while amplitude is constant. Or the other option is we can see those signals where both amplitude and frequency are modulated. That's why it's M. So for modulated with time. So the good example of the amplitude modulation vibration signal is the vibration of transformers you can see everywhere. And the other good example for the amplitude and frequency modulation random vibration signals, you can find it from the vibration of the cars. So we mimic these vibrations from the industrial or our daily life to make those random vibration signals and develop the tool, the predictive tool to calculate the output harvesting performance under these non-stationary random vibration signals. So for that, we also, again, experimentally verified, and as you can see, those experimental results and prediction results, the analytical modeling results are in great agreement, luckily to us. And the other aspect I'd like to emphasize here is that we introduce some statistical correlation metrics so that we can compare quantitatively the experimental results, experimental output performance with the analytical output performance, both in terms of absolute magnitude and the trend. So if you look at those metrics, you can see how much percentage the trends are in agreement or in how much percentage the absolute magnitudes are in great agreement. And that's what we did to look at the other vibration environment for energy harvesting. And also, I've worked on the development of high-performance piezoelectric materials for energy harvesting. So there was a low-loss piezoelectric single crystal fibers that was used for piezoelectric and magnetoelectric composite, as well as a composite energy harvesting as well. And right now, I focused on the I focused on the electrospinning technology to produce the piezoelectric nanofibers, and it's just an ongoing stage. So I'm not focusing today here, but I'm also working on the materials here. That's what I wanted to emphasize. So far I've talked about the structure or materials aspect or the theoretical modeling of the energy harvesting itself, energy harvesting conversion or the management part. So those are the conventional things. So as you see from the title, now it's time to talk about the metamaterials related energy harvesting. So you look at the mechanical waves. There are so many kinds of mechanical sources. Depending on the input mechanical sources, it has different frequency levels. So these are all mechanical waves. I'm looking at these levels of frequencies. And the conventional energy harvesting systems, as I addressed so far, what we focused is the high efficient devices and materials for efficient energy conversion and high efficient circuits for power management. But what if we can amplify those input energies around, like these mechanical waves, into the desired point and then convert them and then manage them? And that's what we thought, and I think that there are a lot of people out there who thought the same way. So the analogy is like this. So if we have I think you've experienced this, you had an experience like me, like this thing. So you have a paper probably in your childhood, and you cannot burn the paper just with the sunlight. But if you have a magnifying lenses, you can focus the sunlight into the spot you want, and then you can burn them because the energy is focused. So what if we can have a magnifying lenses like that for mechanical energy harvesting? So metamaterials are the magnifying lenses for us like this. So that's a new paradigm because we are focusing on amplification of input energy even before the energy conversion occurs. So this I want to call it a new paradigm, but I started to call them like a new paradigm a few years ago. So I'm not quite sure for now it can be a new paradigm. So I'd like to introduce the concept of metamaterials before I move to the metamaterials-based energy harvesting. So when I came up, when I saw the word metamaterials, I was curious because metamaterials are new material. People said it's a new materials, but they said we can make it out of conventional materials like aluminum. So I looked it up and I realized that meta means beyond. And material means not the materials, it's a material properties. So metamaterials are defined as the artificially engineered structures that can exhibit some unique properties, that unconventional properties that we cannot see in nature easily. So it's just we can make metamaterials out of conventional materials, but it's more of a structures, and dynamically within some specific ranges, you can observe some negative or even zero mass density or modulus. If I can have a negative mass density, that would be really ideal for me to when I weigh myself. And these are the matter. If it has, it can exhibit these material properties, unconventional material properties. In broader meaning, we call all of these structures metamaterials. So to give you some feeling about the metamaterials in mechanical wave ranges, I put this slide here. So Professor Nicole Fang talked about the optical ranges. So it's closely related to nanophotonics because the frequency is like this high and the wavelength is related to unit cell of these these metamaterials. That's why it's closely related to nanophotonics. But in ultrasound or in acoustic waves, even in the bigger seismic waves, we look at the scale we look at is centimeters or millimeter scales because the frequency is about these 70 kilohertz or 7 to 9 kilohertz, even below 1 kilohertz. That means we have a much larger wavelength. That means we have a larger scale of metamaterials. So this is the comparison of the waves depending on the sources. So in terms of the mechanical metamaterials, in a broader meaning, we call all of these like metamaterials, but sometimes we strictly categorize them into several kinds. So the representative two are demonstrated here. The first thing is phononic crystals, and the phononic crystals are periodic arrangement. So like similar to any periodic arrangement, it can have a band gap, even though it has different sizes. So once the waves propagate here, it cannot propagate further within the band gap within the certain range of frequencies like here. Or if you use it, so this is due to the Bragg scattering. But in this case, in acoustic or elastic metamaterials, we use the concept of local resonances. I'm not going into detail here, so today I'm going to focus mostly the phononic crystals, but we are working on the acoustic metamaterials also based on local resonances. And the phenomenon we can observe out of the metamaterials, not only the band gaps, the other thing is the negative refractions. So the meaning here is that the band gap means energies go into the structures and they didn't go propagate further. That means energy is trapped inside the phononic crystals. That means we can use those trapped energies because they are highly densified. And the other thing is, if we can control the direction of the refraction, not only the positive, like in conventional materials, if we can control the direction into negative, then we can focus them into certain point. And that's why we can use these metamaterials using these wave manipulation capabilities for energy harvesting. And other than energy harvesting, what we can look up is as applications of sound and vibration insulations and acoustic lenses, super lenses, and hyper lenses, all those things. If you are really interested, there are so many nice review papers regarding these acoustic metamaterials. And one of our speakers for my Connect series, he was the author, and I recommend this paper a lot. And so, yeah. So from this point, I'm going to talk about what we've done in terms of metamaterial-based energy harvesting. So the first thing you can think of easily, intuitively, is the energy localization inside the phononic crystals. So energy is trapped inside the periodic arrangement and the phononic crystals. And if we remove one unit cell, so create a defect is always unstable. So the unstable positions, the energy can be localized at that point. Then what we can do is we can locate the piezoelectric films or piezoelectric devices to harvest them. And that's what people did in the previous works like here. So vibration cases and sound cases and elastic waves, the solid waves in the plate. But the thing is here, the absolute magnitude of the power generation, the amplification ratio is very high, but the absolute magnitude of power is not very high, like a nanowatt or microwatt. And the other thing is the cylinder type, the hole type, all those things are very intuitive designs. So just very simple designs. This is good, intuitive and very simple designs, good. But we came up with this new designs, which is octangular hole type unit cell designs, so that we can maximize the band gap with a center frequency of 50 kilohertz here. So we performed the size optimization, and then we got the parameters, and then with the center frequency, and we could broaden the band gap size like here. And we calculated of the designed supercell phononic crystal supercells like here, and as you can see, we have a band gap with a center frequency of 50. So if you look at here, we perform the harmonic analysis, and you can see that once plane waves go through, the supercell is here, and at 40 kilohertz, which is outside the band gap, and so we can call propagation band, it goes further. But inside the band gap at 50 kilohertz, you can see that the wave propagation is prohibited. So energy is trapped. Then what we did next is we create a defect like here. So we didn't make the hole, and that's the defect inside here in this regard. So in the supercell, the defect is here, and when we perform the harmonic analysis, you can see clearly there's an energy localization, and at the center with a maximum level. And if we calculate the band structure here, you can see that still band gap exists, and defect band is created. So we can use this defect band, and we fabricate using laser cutting. And this is the holes, the octagonal holes, and using 2 millimeter thick aluminum plate to make the phononic crystals. The reason why we chose aluminum plate, a lot of people who are working on elastic wave research, related research, we normally use aluminum plate. There's a reason. The reason is, aluminum plate is we know properties very so we know properties of the aluminum plate very well. So most of the properties are known. That's why once we make some certain different some new when we introduce new structures, then we can differentiate the newly introduced phenomenon out of the existing material properties. That's why people use aluminum when we try to evaluate those metamaterial performances. So before I go, so at the center, so this is a defect. So at the center, we attached a piezoelectric devices, which is commercially available. I'll talk about it a little later more. So this is our initial setup. So that was our first time to do the experiment with the phononic crystals with elastic things. So the first thing we should do is we have to generate elastic waves. For that, we attach the piezoelectric transducers here, and then they can generate elastic waves and propagate here. And in order to visualize the wave propagation before the supercells and inside the supercell and outside behind the supercells, we used laser Doppler vibrometers so that we can scan the whole mechanical displacement. And lastly, and most importantly, we measured the energy harvesting performances using the simple circuit conditions. And I have to emphasize here that you might be surprised with this big size of our specimen. The reason why we use this big size specimen is we want to make the environment like an infinite propagation of waves. So if we have a finite size of the specimens, then it can induce reflected waves. So it's really hard to see the pure behavior out of the metamaterials. That's why we use the infinite plate as much as possible. So from the experimental, like in simulations, what we can see is that before, if it does signals go from this way, and when signals go this way, experimentally, we could visualize the in-plane wave generations like here, beautifully. And inside the defect, you can see that there's a donut-like energy localization. So like if you can see myself, like this way, the Z directions, there's a pop, so up and down motions. So we attached the piezoelectric energy harvester later here. And behind the phononic crystals, you can see that there's little wave propagation, which means we have a band gap working. So a few of the waves are from reflected waves from the boundaries I already mentioned. So we looked at the energy harvesting performances, and when compared with the energy harvesting devices without phononic crystals, it has an amplified voltage output, like about 4.8 times in terms of voltage, and even in power, power even more, so more than 22 times. And the most prominent part is that we got the about milliwatt level of elastic wave energy harvesting. If you're familiar with like triboelectric energy harvester or the vibration-based energy harvesters, it's easy, not easy, but you can see easily about the milliwatt level of powers a bit. But in elastic waves, it's really rare. So it was, as far as we know, it was the maximum level of power from elastic wave energy harvesting. And that was our kind of first work with metamaterials for energy harvesting. And in parallel, we performed some parametric studies to see the effect of supercell size and the defect location, the effect of defect locations. So what we found here is that when we increase the supercell size, we expect that the degree of energy localization gets increased as well. But in the other ways, unlike we thought, after the certain size of the supercell size, it just reaches the saturation level, so we don't have to increase the supercell size too much. And the other thing is, if you look at the defect location with the same size of the supercells, you can see that at the second part, it doesn't guarantee, because we only have one layer from the incident. It means that we don't have a periodicity yet. So that's why the energy is localized that much. But at third position, in the third column, you can see the energy is localized very well. But after that, it's because of the attenuation, the energy level is getting down again. So there's an optimum position for defect location as well. That's what we studied here. And also, we are not only limited to the creation of a single defect. We studied the interaction of double defects inside the supercells. So once we introduce two defects inside the supercells, if it's not too far from each other, they interact with each other. The result is that we have a defect bands like here, using a single defect, like 6 defect bands. But these each six defect bands are split into each other, so total 12. So this is a very interesting physics, and then you can see that at the, especially with an example of target defect band frequency about here, is split it into 2 like here. They show a monopole-like defect mode shape, but at one frequency, 59, about 59.7, the mechanical displacement appear in phase, while at the other frequency it shows out of phases. So we can use them we can use them differently when we attach the piezoelectric devices on top of these two defects. So we can vary the types of electrical circuits connected to each of piezoelectric devices, and depending on the type of the circuit connections, we can generate different levels of power out of these two defects using phononic crystals. So far, I've talked about the energy localization using phononic crystals. Now, I'll talk about the control of directivity of the wave propagation. For that, what we can do is we can vary the refractive index n, which is directly related to the wave propagation velocity. So if we vary n, that means we vary the velocity. That means we can bend the waves depending on the position and depending on the n values toward the focusing point. So that's why we can use green lenses or green metamaterials or green phononic crystals. So this is elastic energy harvesting. So we designed we use the genetic algorithm for optimization so that we can get the radius size of the holes, so that we can design the whole elastic green lenses like here, and we fabricate it using aluminum plate again. So, and we looked at the wave focusing capability first. If you look at the simulation, you can see that there's a focal point here, and then there's a focal area a little bit distributed. And considering the manufacturing tolerance, we rounded off the net values of each design parameters, and we looked at it, the performance, the focusing capability is still maintained. Experimentally, it's confirmed as well, and they are in great agreement. And since we have now focused energy at the focal point, what we did is we attached the piezoelectric device on top of the focal point, and we compare those energy harvesting capability with and without green structures. And there are 2 points I'd like to make here. The first thing is using green phononic crystals, what we can do is we can control not only the amplitude, but also the direction of the waves, so that we can have a direction controllability. And the other thing is, unlike the phononic crystals, like this is our work here, but unlike the phononic crystals, in terms of power density, it has a very advantageous aspect. So when we divide the output power by the area, effective area, we have a really, really highest power density. So far, I've talked about the elastic wave energy harvesting. Now I will talk about the sound related focusing and sound energy harvesting. So here again, we looked at the green. We wanted to use the green structures, but the problem is that depending on the input sources of the frequencies, the focal points appear at different places, which is called chromatic aberrations. It happens in optics as well. So in order to solve this problem, we came up with this idea of adding coating layers, like chromatic coating layers, which can be topology optimized, like here. So using topology optimization, we could identify the distribution of the material ABS or air. We use air. So if we add these two materials, as you can see from the simulation results on the right side here, when we add these coating layers, the focal points invariantly appeared regardless of the frequencies, unlike the conventional cases. And this is experimentally observed as well, nicely. So the green structures, acoustically rigid materials, aluminum were used. And for coating layers, we use ABS using 3D printers, and we use the acoustic waveguide to make plane waves that can be applied toward the green structures. And these are the experimental results. So the upper top shows you the results, the relative sound pressure map without the chromatic coating layers, while the bottom map shows you the very achromatic behavior of the green lenses with achromatic coating layers. And I have to say that this is a featured article, and this article is published this week, so you can find it now online. I'm very proud of this work, and I'm going to go to the next level. So the other thing we looked at with we wanted to using sound wave energies is omnidirectional focusing and harvesting. For omnidirectional, as like intuitively can think of, there's an optical black hole, like a black hole really. So electromagnetic waves come in and they are trapped at the center. And there's an acoustic counterpart to this. And so there's an acoustic black hole observer. We adopted this idea to have the omnidirectional focusing and harvesting. So we designed the structures by varying radially the refractive index, and we adopted the circular symmetry so that we can have omnidirectionality. And in harmonic analysis, you can see that at the center, the energy is focused, the sound energy is focused. And this article is published this week too. So, the design we have, we fabricated using ABS like before, and we customly made the acoustic duct system to evaluate the sound pressure at the center of the omnidirectional phononic crystals at the center, and without it too. So when we compare the sound pressure of the omnidirectional phononic crystals with nothing, then you can see that there's a amplified sound pressure. You can see the sound is amplified with in a wide range of frequencies, especially at around 800 hertz. There's a maximum amplification occurs. And experiment, the same thing can be observed. And at the focused point, we put the try to characterize the harvesting performance using these omnidirectional phononic crystals. So we located the PVDF, the piezoelectric polymer film, on the bottom of the omnidirectional phononic crystals, and we could find that there's a power enhancement up to more than 7 times. And since we use the piezoelectric polymer commercially available in film, if you can use a device with high performance piezoelectric materials, there's a more further room for further enhancement. And if we looked at the impedance matching between the air, and the structure, and we can further improve the energy harvesting performance using this omnidirectional phononic crystals as well. That was about the sound energy harvesting. So I have to check the time. I guess I'm out of a little bit of time. So far, I've shown you various types of metamaterials, including phononic crystals for energy localization and gradient refractive index type to alleviate the directional property. But the other way, on the other hand, we have to look at the interface between the metamaterials and the energy harvesting devices, which has not been done at all so far. So metamaterials is a really in an early stage of research, and then this metamaterial-based energy harvesting is more early stage in research, I guess. So we looked at the interface, and what we found, I will make a brief summary here. So what we found is that instead of just using big piezoelectric energy harvest, like big diameter or thick piezoelectric ceramics like here, we have to consider the mechanical impedance, that we have to consider the trade-off because between the voltage generation and the impedance mismatching thing, or we have to think about the voltage cancellation effect because of the wavelength size. And depending on the phononic crystal size, the unicell size or wavelength size, we can determine the sizes of the energy harvester to enhance the energy transfer at the interface. And like in vibration energy harvester, the product of a high piezoelectric coefficient D times G is the best for the best performance of energy harvesting using phononic crystals as well. I think I have to wrap up somehow. So far I've talked about the energy transfer and things here. So this is a summary thing. So today I showed you several concepts of metamaterials for energy focusing and energy harvesting. So elastic regimes, you can see the phononic crystals and gradient things for sound in here. But the current work we are working on is that the current topic we are working on is meta surfaces, because these structures are very large. We really need to reduce down the sizes if you want to carry the portable metamaterials, or if we want to install very easily. So what we think of is that we can use local resonant materials, metamaterials based vibration structures or meta surfaces that can give us some sub-wavelength scales. That's what we are working on right now. And once we develop a new metamaterial designs, what we have to do is that we have to integrate these metamaterials into energy harvesting systems. For that, we have so many nice collaborators who are experts in piezoelectric energy harvesting materials and devices, also circuits. I'd like to give you some of the future directions about. I already mentioned the broadband operation of the energy harvesters, but it applies the same to the metamaterials. We really need a broadband operation of metamaterials. For that, we can look at some other innovative metamaterials designs. Or, as I said, we really need a size reduction. For that, we can use some meta surfaces or mechanical metamaterials that I couldn't cover today. And once we look at in terms of the metamaterial-based energy harvesting perspective, we have to think about the impedance, because there's an interface, and then even if we observe too much energies out of the amplified energies through the metamaterials, if we cannot go through the piezoelectric devices, then we cannot obtain the electrical energy as much as possible. So we have to think about we really need interface studies, and we really need the target applications using metamaterials devices. I'm a little bit late to include all of the my collaborators, but these are part of them, and then we are happily working on the energy focusing and harvesting systems all together. And I'd like to wrap up with a comment with my favorite phrase, milliwatts with mega impact. I always put this slide at the end. So energy harvesting technology is something that gives a very small power, like milliwatts, but I strongly believe that it will bring really a mega impact in the world. So, when coupled with metamaterials, I believe we can make a broad impact on the world, and then we can contribute to the world technology. Thank you so much. I'm sorry for being a little bit behind, 5 minutes later.
Yes, we are ready for the question and answer session. Hold on. I can see them big enough to read them here. I need to switch to a different view of at the scan. Okay, well, now I can see the question, and let me read it for everyone. Dr. Kim, for using defect in crystals to harvest the energy, will it damage the materials in long term?
Oh, the defects. So
the defects in the crystal, yes.
Yeah, the feeling from the term defect means we have something bad, but the defect here is that we don't introduce unit cells as usual. So if you think about the hole type unit cells, we have no holes, and I don't think it will damage the whole performance because of the introduction of the defect itself.
Thank you. And normally defects are unexpected, and we try to typically avoid them in real materials. How to make the device work in this case of uncertainty and presence of defects?
So if you're a material scientist, you might be familiar with eliminating defects, but this is I showed the slide which shows the scale of the wavelength, because this is a different scale of structures. So what we call defect is a very like purposely introduced one, and this is a very carefully designed unit cells. I don't know how to say that. So, so this is not something that happens without planning. So this is an intentionally introduced unit cell design. Defect is also a design. So you can think of a ononic crystal with a defect is a combination of two unit cells, two different unit cells. So a majority of unit cells and one type of different unit cells. So this is not something different. I think this is a bit different from the defect that we think of in material science that we want to eliminate. Hope this answers the question.
We have probably time for a couple of more questions. Another question is whether the elastic energy harvester can work also at lower frequencies.
Oh, so in the last slide, I showed the vibration level of so low frequency metamaterials. So that's a very low frequency elastic metamaterials, but I tried to categorize those sources. So it can use the vibration structures, the whole structures like this, but at low frequencies in elastic regimes, it's still the solid waves can go through and we can use them. So a lot of questions I got so far regarding the elastic waves, wave energy harvesting utilizations. So people ask me, where are those elastic waves? So if you think about the shock waves from the bridges, so we measured actually the elastic waves, the components, the frequencies and the amplitude from the bridges and on the roads and the buildings. You can find everywhere from the industrial site or on the infrastructures. There are so many low frequencies or high frequency elastic wave sources. So you can use them also. And elastic waves we can use at any frequencies, but the thing is we have to think about the size, because the size will be larger and larger. So we have to think about some innovative ways.
Thank you. And we probably have time for 2 more questions. For the acoustic harvester, can it be used in a cell phone or another handheld device for daily applications? Can it be made small enough and produce enough energy?
I have to be really honest here. So the least energy generated, the various mechanical source that can generate the least level of power is unfortunately sound. So sound energy is really has a very low density. So that's why we focused, but the sound is everywhere. So we want to use them. But the problem is so far, what we have as omnidirectional or chromatic things like in this big. So you don't want to you don't want to attach these big sizes of structures on top of, in addition to your cell phones, because you want a smaller cell phones. So what we think of right now is that we want to use some smaller sizes of the sound focusing and harvesting. But I think we need some time to make them portable and then additionable to the cell phone. I don't want to carry that big one yet. So, but the realistic environment we can think of about the sound energy is the like a stadium or the road, expressways or those things. So once we have a wave manipulation capability, not only the wave focusing, we can think about the wave manipulating or to attenuate those sounds or those things. So rather than addition to cell phones, I'd like to think of some more realistic applications. But I think it will take some time, but I make sure that I will make some sound focusing metamaterials for your cell phone. I don't know who asked that, but I keep that in mind. If I can reduce down the sizes.
Thank you very much. My last question, actually, personal, would be here. To what extent using nanomaterials, two-dimensional materials, you can improve design of harvesting devices and design better metamaterials?
In terms of 2D materials. We adopted a lot of the concepts of metamaterials, the acoustic and mechanical metamaterials, out of those phononic crystals existing in semiconductor materials. A lot of the intriguing concepts came from actually graphenes recently. So there's a topology acoustics related. The field of topology acoustics is related to 2D materials, and we adopt the idea from the physics of 2D materials. And then now I think we are in the stage to move forward to making those 2D materials integrated into the metamaterial system, not only just mimicking some ideas out of the structures of the 2D materials.
Thank you very much.
Yeah.
Well, again, we are presenting this certificate, a virtual certificate to you. You will get, of course, an electronic copy. So congratulations. Thank you very much for opening our ACS Nano Rising Star Talk series.
Thank you so much. And this is an honorable event. I'm really enjoying a lot. And thank you so much, Alex and Yuri and Paul and everybody. And thank you to the audience who's staying with me tonight. Thank you so much.
Wonderful. Am I coming through there? Very good. So it's my honor to introduce Professor Nanshu Liu, who is an associate professor at the University of Texas at Austin in both aerospace engineering and engineering mechanics,